All right, everyone. This is Mr. Lee. In this video, we're going to go over the main ideas of center of mass. Now, at the beginning of this unit, we did talk about center of mass, but now that we have gone through the entire momentum unit, we can probably look at it with a little bit more detail. So let's begin. Okay, so the idea of center of mass, okay, or I might just write it as COM a lot of times, is the average distribution of an object slash system's mass. Okay, and I'll show you exactly what it means between the two, or the distinction that we can make. Okay, so it's important to know that if we just have a point particle, right, so just like a little dot, and that dot could represent like a ball, it could represent a box, it could represent a lot of different things. That is what we call the center of mass, right? So when we draw things, right, oftentimes in physics, we don't actually draw the person, or we don't draw the dog or the car. We represent it as a dot. And that dot actually represents the center of mass. So the idea of the center of mass is if you get like, let's say, a ball or like a car, and you were to like crunch it down into a tiny little ball, that would be the idea of center of mass. So you just take the entire object and just smoosh it down into a little fine point. So this right here would be the center of mass. Now it's important to know that when we are talking about the center of mass, the important idea is the location of the center of mass. So we will say the center of mass is located at that point. So this is example one. There's another example. What about like a donut or a hoop? All right, so this is like a hoop, and we know that in the middle of the hoop, it's empty, right? The hula hoop or like a donut has most of its stuff on the outside. But if we were to crunch that hoop down, the average location of all of the hoop will be right there in the middle, so that right there in the middle, that would be the object center of mass. Even though there's actually nothing located there, that is where the center of mass would be if we were to crunch the hoop and down into a fine point. So it's the average distribution of the objects slash the system's mass. Okay, so let's take a look at a different scenario. What about a system? So I'm going to represent the system as this box. So whatever is inside this box will be considered the system. If we have a object here and an object here, the center of mass would be right there where the X is. Okay, that kind of makes sense, right? So the average distance between the two is right there in the middle, and we're assuming that the two objects have the same mass. So same mass, and the middle part, the middle distance, right, or the average distance, would be the location of the center of mass, which is right there. Okay, so let's take that same idea, but let's make one more massive. So if we make the left object more massive, okay, compared to the right one, the center of mass will be, on average, closer to the area with more mass. So more mass located to the left. So the center of mass is towards the left. All right. So with this idea of center of mass, we can actually get into the idea of the center of mass and the center of mass's momentum. So let's do the same ideas, but now let's apply the idea of the center of mass, or the system's velocity. So we said that if we had a point particle, right, and the center of mass is right there, and it had a velocity, right, it would have the object's momentum. So for example, if this object had a mass of 1 kilogram and was moving to the right with 2 meters per second, we would say that the momentum would be 2 Newton seconds, right? And this is just what we've been practicing. Now, what if we have the hula hoop scenario? So with a hoop, okay, we don't have to take a look at the hoop in its entirety. We could just look at the center of mass. And once again, the center of mass would just be right there in the middle. And so let's say that the hoop overall, so the mass of the hoop was 1 kilogram, and the hoop itself was moving with a velocity of 2 meters per second. That means that we will say that the momentum of the hoop would be 2 newtons per second. So we can see how even though the object itself is different, okay, numerically it comes out to be the same momentum. And so we could write it like this. We could say the mass or the center of mass for the hoop is still going to be 1 kilogram, okay, because it's just that one object. The velocity of the center of mass, because if we're saying that the hoop is moving to the right, the center of mass is also moving to the right, is, let's say, 2 meters per second. We could say that the momentum is still 2 newtons per second. All right, now what about a system where we have, let's say, this object here and here, okay? And we'll say both of the objects' mass is 1 kilogram each, okay? And we identified that the center of mass will be right there in the middle where that X is located. And so the center of mass, remember, is the average mass of the entire system. And so, excuse me, the total mass of the entire system. And so the center of mass would have a mass of 2 kilograms. Because we will look at the system's mass overall. But now, if we take a look into the idea of momentum, if we say that the object on the left is moving to the left with a velocity of -2 meters per second, but the object on the right is moving to the right with a velocity of 2 meters per second, now we can look at how the system's momentum or the center of mass's momentum is affected. So we can say that the object on the left has a momentum of -2. We can say the object on the right has a momentum of +2. So if we take a look at the system overall, we can say that the overall system's momentum, okay, so momentum of the system is equal to 0. And we got that by adding -2 with the +2. So this tells us a lot. What this tells us is that the momentum of the center of mass is also going to be 0. Okay, so what that shows us is, let's say initially the object was right there and right there, right? But as time moved on, this object went from the starting position here and it traveled to the left here. But because they had the same velocities, this object that was here, after the same amount of time, moved over to the right with the same amount of velocity. So if the average center of mass was here initially, it doesn't matter that the two are further apart. The average center of mass would still be in the same location. So because the object center of mass did not move, we can also say that the object's momentum or the system center of mass is also 0, which means that the velocity of the center of mass is also going to be 0. The center of mass does not move. And we'll take a look at an example problem for that as well. All right, and so that's the big ideas behind it. And we'll take a look at different scenarios and some advanced scenarios that you will need to know for this unit. So let's go ahead and take a look at a couple of simulations so we can take a look at the things that we just discussed, what we just witnessed, right? All right, so for the first scenario here, let's take a look at this. These objects both have a mass of 1 kilogram that you can see in the data table, and they are both moving with the same speed. One, of course, is moving to the left, and the other one is moving to the right. So the total momentum of the system will be 0. So keep an eye out on that X in the middle. That X in the middle represents the center of mass. And if we know that the momentum of the system is 0, that center of mass should not move. So here we go. Oops. Let's return. All right, there we go. Even after the collision, it does not move, right? Just like we discussed. One more time. Very good. All right, so one of the other things that we discussed is, what if one of the objects has a bigger mass? And if we take a look at that, remember what we said, the object with the bigger mass has the center of mass geared towards it. So if I change object 1 so it's more massive, we saw how there was a shift of the center of mass to the left, okay, towards the bigger object. Now, when I push play on the simulation, because I changed the mass of object 1, it now has a different starting momentum. So let's take a look at the table. We see that object 1 has a momentum of 6, and object 2 has a momentum of -2. So the center of mass has a momentum of +4. So what this means is that the X will be moving towards the right even after the collision. So let's take a look here. It's moving to the right, post-collision is still moving to the right. Okay, so the average distribution of the mass, you can't see it because the ball went off screen, but as the ball on the right is moving further and further away from object 1, the center of mass is also adjusting itself, as we can see there. All right, the other one I want to show you, this is what we call a explosion type of situation. And so this is a different simulation here. But what I want to show you here is that we have two objects. Okay, we have a red object or the small object and a blue object, which is the bigger object. And the center of mass is more towards the bigger object, right? So the blue object. And this shows you one of the things that we discussed, where the center of mass was within the system itself. And so it's not in between the red object and the blue object, but within the blue one because it's more massive. So I'm going to push run. So when I push run, you can see that after the explosion, which happens right about now, okay, the center of mass is still moving with the same initial momentum. It doesn't matter that there was an explosion because there was no outside forces interacting with the system. Therefore, the center of mass's momentum will not change, even though the individual momentum changes. So here's something cool about the simulation, right? The simulation here, it shows you a velocity chart here. So we can see that initially in purple, they had the same velocity, but after it, it's kind of hard to see. It's a little bit small, so I will make it a little bit bigger. There we go. Push run. That's there. The velocities also change upon explosion. So it's going to explode right there, but we can see that the average will still be where the initial velocity was. So that shows you that the system's center of mass's velocity is still where it was to begin with. All right, the other one I want to show you is called the Raft problem, and I'll break this one down. I'm not going to draw the person in the raft, but instead when I do the problem, I'm going to draw it with the dots, the center of masses. But I'm going to show you something here. This is a classic problem. So in this problem, let's say you're in the middle of the lake, there's no waves, right? So there's no outside forces, just you and the raft. And the question then becomes, what happens when you walk forward on the raft? Okay, what will the raft do? And the question gets even deeper, and it'll ask, where will the raft be located if you walk to the end of the raft? Okay, so this simulation will show you exactly what happens there. So there's a couple of things I want to point out. Okay, the initial momentum of the system will be 0. So we're both starting off at rest. And then after I push play, then they will have a momentum. But the overall momentum of the system will still be 0. So what that means is that person moves to the right, therefore the raft moves to the left. But once again, it's important to know that the center of mass will still keep the initial momentum of 0. All right. Also, I want to show you here that if I increase the mass of the raft, we can see that the center of mass of the system gears it towards the raft. Okay, but we'll make it the original 200 there. All right, so I'm going to push run. If I push run here, you can see that, yes, the raft moves to the left, but the center of mass of the raft person system doesn't change. And now the person is doing a moonwalk, and we can see how it moves it backwards. It's also important to know that the motion of the raft and the motion of the person isn't necessarily the same, but the overall momentum is still going to be 0. All right. Now, the only way that the two motions will be the same is if we have them have the same mass. So what that means is that if they have the same mass, there's going to be an equal change of position for the raft as there is for the person. Okay, so if the person walks forward a certain distance, the raft will also move back a certain distance, the same distance. But if I were to do extreme, right, if I make the raft super massive, we can see here that even though the person is moving a lot, the raft itself is not moving by that much. Because remember, momentum is mass times velocity, and the momentum of the raft, which has a big mass, needs to have a smaller velocity. But the person has a small mass, so it'll have a bigger velocity. All right, and we're going to go back to the drawing board. The raft problem. So the raft problem, the system is the person and the raft. So if you're taking some good notes here, the key here is that the center of mass of the system will not change. Okay. Now, I'm going to put a little caveat here. The only time that the center of mass is change its location is unless there is a outside force. Okay, and that outside force, that term, we use it in the energy unit, and when we say there's an outside force for the energy unit, we say that there was work being done. But for momentum, this means that there is a impulse. Okay, if there's an impulse acting on the system, then the center of mass for the system will change. But until then, it'll remain where it is. So here's some very important ideas. The velocity of the person is 0. The velocity of the raft is 0. So the velocity of the center of mass is 0. Therefore, the momentum of the center of mass must be 0 no matter what. So strategies. And this goes for any type of problem where you need to be looking at an explosion, a elastic situation, an inelastic situation. It doesn't matter what. Okay. So situation 1 is you need to be able to locate the center of mass. Step 2, determine the momentum for the center of mass. And then step 3, double check, right? Make sure there is no impulse, right? If there's an outside force, then that does change things up, right? And so the final step is the final position. The final center of mass will not change. So locate the two objects accordingly. All right, so those are the steps, and I'm going to walk you through it. And instead of drawing a raft and a human, I'm just going to draw different circles, okay, as objects. So here we have object 1, and we'll say that this object has a mass of 10 kilograms. We'll make it nice and easy. And here we have object 2, and we can say that this object here has a mass of 2 kilograms. And we'll say that the center of mass, right, and this is very conceptually speaking, will be located right here, close to the 10 kilograms. So what I like to do is I like to, instead of going side to side to show progress of time, right, so here this is time 0, I like to go in a vertical direction. But before we do that, let's give this velocity of 0, and this here is a velocity initial of 0. Okay, so nothing is moving, nothing is changing. But, and these two are connected, just so you know. All right, so there is a connection. And remember, this is just my sketch of the person on the raft problem. I didn't draw the person, and I didn't draw the raft, but those two circles represents the raft and the person. All right, so the person is going to be the orange person or the orange dot because they are smaller than the raft, right, according to the scenario. And so in, let's say, time, let's see, greater than 0 seconds, the person is now moving to the left. So let's say the object is now right here. Okay, so the object is there, and the velocity is to the left. All right, and so here, let's locate the center of mass, right? So the center of mass should remain there. So that means that if the person came over there, I would say, like, that's probably a good location of the 10 object kilogram. But if we were to do this numerically, let's say the velocity of this person, I don't know, we'll make it negative 5 meters per second. Negative 5 simply because it's moving to the left, right? So that means that the momentum of this person, so momentum is mass times velocity. The object originally had a mass of 2, and the velocity will be negative 5, so the momentum will be negative 10. So that must mean that the blue object's momentum also has to be negative 10. So P equals mv, or excuse me, positive 10, because positive 10 plus negative 10 gives us 0. The object has a mass of 10, so the velocity has to be 1. So the momentum is 10, right? So this object is moving this way to the right, and this object is moving this way to the left. But the center of mass is still there, all right? So here, the center of mass, after much time has passed by, so much greater than 0 seconds, we can say that the orange object, let's say it's over here somewhere, okay? And so if the orange object is all the way over there, we can say that the blue object, probably like right here-ish, okay? Because we want the center of mass to be closer to the blue object, okay? All right, so things to look out for here, okay? Locate the center of mass and make sure your center of mass always is within the same position, okay? And then distribute your objects accordingly. And if you have to do a little bit of math, make sure that the momentum of the system does not change. So our initial momentum was 0 and it remains 0. All right, so the final situation I want to show you is an explosion type of problem. And in this explosion type of problem, we call it the fireworks situation, okay? So in this fireworks situation, okay, we have an object here. And this object is launched at an angle theta with a velocity of v. In the first explosion, right, the firework actually, it doesn't go off, it doesn't detonate, but instead it just keeps on going forward and it lands over here. Now, the important about this here is that this shows the final location of the center of mass, okay? All right, and so you get frustrated and you fire off another firework and hopefully, fingers crossed, it works. So I will represent this next firework here with red. All right, so this next firework, okay, you fire it off, you fire it off, you fire it off, and at the very peak, it explodes. All right, so the question is, okay, if we could locate one of the fireworks pieces and it goes all the way out here, and we can say that this is a length of L, okay, and it lands over here, a length of L away from where it should have landed if it didn't explode. Where did the second piece land? All right, so here's how we solve this. We know that the center of mass should be right there, right? Because there are no outside forces within the system. Okay, so the center of mass was right there because that's where it landed when it did not explode. And we do know that one of the pieces, and we'll say the pieces have equal mass, right? It's split evenly, located a length of L away. So that must mean that the secondary piece must be at a distance L away here. But we can say that's like negative L, right? And so if I were to draw this carefully, I don't know if I would show you that, but this will be negative L. And so the object would have just dropped straight down. So the second piece would be right there because that is a distance of negative L away. And here we have a distance of positive L. Okay, so the approach to solving these problems, the tips is still the same. Locate the center of mass, right? And after the interaction happens, make sure the center of mass is right where it belongs, as if like no explosions happened or no interactions happened. Okay, so this problem can only change, right? So here for this problem, we said that they had equal masses, but what if they did not have equal masses, right? So let's say it should land there, but let's say piece 1, okay, or mass 1 has a mass of let's say 2m, okay. We'll just make it m. We'll make it simple for us. All right. So piece 1 has a mass of m, but piece 2 has a mass of 2m. Ooh, yeah. And so here's what we know. We know that piece 1, let's say it landed, exploded up here, and it landed, say a distance of like about here, right? So whatever this distance is here, d. So that's pretty far away, right? And so if we know that the center of mass should be right there, but it's twice as big, that means the center of mass is closer to the second piece. And so we can say that the second piece might have landed like somewhere here, right? Because this is piece 2, here this is piece 1, and the center of mass has to be somewhere there. And so the path of piece 2 would look like this, and the path of piece 1 would look something like this. It would have shot out like so. All right, so those are the 2 classic problems for center of mass. We'll get a lot more practice in class, but those are the concepts, and I'll see you next time. Bye-bye.